Hi and welcome to this video on the differentiation section of the Year 2 part of the A-Level Maths course, and this one's a biggie, bringing together two big old topics, differentiation and trigonometry. So what we're going to be looking at in this video is using our chain rule to be able to differentiate sine and cosine, and as well as that we're going to have a look at how we deal with powered functions as well. So there's a whole world of stuff going on here, but off we go. To begin with, let's have a look at sine and cosine. Let's just stick to those two functions to begin with. So we've got f of x equals, let's start off with sine x, and let's have a go at differentiating this one from first principles. So there's our standard setup for differentiating from first principles. F dash x equals the limit as h tends to 0, sine of x plus h minus sine of x over x plus h minus x. Standard stuff, and it might be doing something like this, might be how they examine differentiation from first principles in a Year 2 way, by doing it to one of these types of functions. So what are we going to do? Well, the obvious thing that we can really attack or do something with is this bit in here, the sine x plus h, and for that we can use our addition formula. So we know sine a plus b equals sine a cos b plus cos a sine b. So let's do that with this section here. So we end up with that. Now, what we're talking about here is limits as h tends to 0. So we're talking about what happens to essentially cos h and sine h as h becomes 0. And you'll have seen previously, hopefully, that we've got these small angle formulae. So what happens to sine h as h is small? Well, sine h becomes h, cos h becomes 1 minus half h squared. So what we can do is use those substitutions, because as h tends to 0 we are talking about small values of h. So let's just do some replacements there. So our cos h, 1 minus half h squared, sine h becomes h, multiply out the bracket here, there we go, and now we can see we've got a bit of cancelling that we can do. So that's sine x there, that's sine x there, and the other thing we can do is some cancelling with the h's. So if we divide this whole, if we do minus half h squared sine x plus plus h cos x all divided by h, the h cancels there. The h squared, we've got h squared cancelling against the h there, so that leaves us with minus half h sine x plus cos x. And as h tends to 0, minus half of this h here, that will become 0. So this term here becomes 0, and so that leaves us with our limit, which is cos x. So that, as it turns out, is a real nice simple result, that if you differentiate sine, you get cos. How good is that? Now, you could do exactly the same thing for cos x, and again, use the small angle formulae to do the replacing and all the rest of it. I'm not going to go through it, but what you end up with is cos x equals minus sine x, and can I put that little exclamation mark in there, just to make sure you're aware we've got cos x is minus sine x, so we've got some issue with sines when we're differentiating the cosine function. Okay, so there's our two biggies. Start off with differentiate sine, you get cos, differentiate cos, you get minus sine. Okay, right, now let's have a look at how these work when we've got functions within functions, and also the notes popped up there saying that when we're differentiating angle measure, when you're doing any calculation, angle measure is always, always, always in radians, never in degrees. Okay, so differentiate sine ax, let's chain rule it. Here we go, u equals ax, du dx equals a, so there we go, we've got y equals sine u. Differentiate sine, you get cos, bring the two things together using chain rule, and we get dy dx equals a cos u, and now finally just replace the u, so we've got a cos ax. Now, notice what you've got here is, we've got the function staying the same there, we've got the differential coming to the front here, and the trig function itself is differentiated. So again, it's that standard chain rule structure that we saw with the logarithms, with the exponentials and everything else. We've got this this standard results. So here we go. Let's have a go at a coordinate geometry style question using a curve that is a trig curve. So we've got 4 sine 3x minus 5 cos 2x, and we've got to find the equation of the normal at the point where x is pi over 6. Okay, so let's do the differentiating. So dy dx equals, well, let's start off, and I'm going to have a little scribble again. If we wanted to differentiate sine 3x, that's going to become 3 differentiate sine, you get cos, the function stays the same, so that becomes 3 cos 3x. So what that gives us is 12 cos 3x, so that's that bit done. And if we differentiate cos 2x, that's going to become, we've got 2 there, differentiate cos, you get minus sine, so I need the minus sign, and then the function stays the same. So that's that bit. So what we've got now is 10 sine 2x. And again, I've just put that note in there too, because we had a minus there. Because differentiate cos gives us minus sine, we've got the change of sign in there. So it's just one to watch out for. So there's our differentiated function. When x is pi over 6, dy dx is 12 cos 3 pi over 6 plus 10 sine 2 pi over 6. Work all of that out, and we end up with 5 root 3. And so we want the equation of the normal, so we need minus 1 over 5 over 3. So the gradient of the normal, minus 1 over 5 over 3. And again, that gives us root 3 over 15. You'll notice that your calculator's just rationalised the denominator if you just put that into your calculator. So that's what's going on there. And therefore, I now need the y-coordinate. Again, at the point where x is pi over 6. So let's get the y-coordinate. Again, put pi over 6 into there. It turns out that the y-coordinate is 3 over 2. And now I've got enough to come up with the equation of the normal. Y minus y1 equals mx minus x1. Bang in the values, and there you go, the blue box has appeared because it doesn't say anything about the format that we need, so I'm quite happy just to leave it in that format there. There you go, there's the equation of the normal that we were after. Okay, so simple example of differentiating sine and cos. Let's just move on a little bit now and have a look at what happens when we differentiate powered functions. So we're differentiating trig functions, so we've got something that's to a higher order power. So for example, y equals sine to the power 5 of x. Again, if you come across anything that is not entirely standard, that you've not seen before, your go-to mechanism is going to be chain rule. I lost my mind for a second there. Because again, we've got a power function inside a trig function. So if you're not sure, chain rule it, formal style. Here we go. du dx cos x, y equals u to the power 5. So that gives us y equals, so dy du, sorry, is 5u to the power 4. Put the two things together, and we end up with that. And so now just reverse the substitution, and we end up there. And if we have a look at what we've got going on there, again, we're seeing a very, very similar standard-looking structure, because what we've got is bring the power to the front, that's the 5. Differentiate the function, that's the cos x. Leave the original function unchanged, our original function being sine x, and take one off the power. So that's exactly the same structure as we had when we were differentiating earlier in the course. For example, ax plus b to the power of n. Exactly the same type of structure. So, like I say, if you're looking at this and you're not quite sure, chain rule it. But if you've done a bit of practice, you know what you're about. It's reasonably straightforward to do it by inspection, but just make sure you don't miss off any of your important bits. Okay, so here we go. What we've got now is an exponential function with a powered trig function as the power. Oh my word, that looks like an absolute mess. And again, that's what I was saying previously. It looks scary and horrible, but we will just go about it formal chain rule style and see what happens. So here we go. This time let's let the substitution u equals cos squared. So now we need to do cos squared, which we could chain rule again, but the principles that we talked about in the previous slide to differentiate that. So du dx is bring the power to the front. There's the 2. Differentiate the cos, minus sine. Leave cos alone, and then take one off the power. So we end up with that. So there we've got a kind of chain rule within a chain rule type of deal going on. So that's du dx. Remember, this is the thing that we're trying to differentiate because we need the gradient so we can work out the tangent. So we said let u equal cos squared. So that means I've now got y equals e to the u. Dy du equals e to the u. So that gives us dy dx is minus 2 sine cos x times by e to the u. And u, reverse the substitution, cos squared x. So that's our gradient function, which is a whole world of trig and exponential functions. But let's not get freaked out about it. Let's just kind of proceed as per normal. We've got an x-coordinate of pi over 4. So we're going to need gradients of the tangent, and also we're going to need the point on the line, so we need the coordinates of A. So at x equals pi over 4, coordinates of A, so y equals e to the power cos squared pi over 4. Cos of pi over 4 is root 2 over 2. Square that, you get a half. So that's that bit sorted. Gradient function, dy dx, is, here's our function down here, so let's put pi over 4 into there. There it goes. Sine pi over 4 is 1 over root 2. Cos pi over 4, 1 over root 2 as well. So we've got, well, 1 over root 2 is the same as root 2 over 2. So that's what we end up with. And you can see we've got minus 2, root 2, root 2. So those bits there times together to make 2. So all of that kind of cancels out quite neatly. And what do you know, we end up with our gradient is minus e to the power half. And so now if we go y minus y1 equals mx minus x1 and put in the values that we've got, so that bit there, there's our y coordinate, there's our gradient. Okay, so far. Now the question says it cuts the x-axis at B, so we've got this point B which is there where y equals 0. So if we put y equals 0 in, we end up with minus e to the half bracket x minus pi over 4. Divide both sides of the equation by minus e to the power half, and we end up with a 1 there. And then get it saying x equals, and there you go, x equals 1 plus pi over 4. Now, the result we're after, we're told, is this one here. So if I just kind of do a bit of tidying up and take out a factor of a quarter out of there, so if I go for a quarter, and what have I got inside my brackets? Well, that bit there is going to be pi plus a quarter. What am I going to put here such that I end up with the value of 1? Well, that thing has got to be 4. And so therefore, we've ended up with the results that we're being asked for. Let me just get rid of that. And there you go. Jobs are good.